Great. Okay. I hope everybody's doing well. Hope you had a good weekend. Are there any questions, any particular problems anybody wanted to talk about before we get started on some combustion problems? Okay. Sounds like the answer is no. So I'm going to go ahead and start working on a couple of ALEKS problems. Looking over the topics in the chapter, the next thing that we want to work on, because we've talked about mass and moles and numbers of atoms and numbers of molecules and such. The next thing we want to work on is elemental analysis. So this is section 3.5. And it's elemental analysis. Okay. There's a little bit of it at the end of 3.4. So if you're looking in the textbook for this material, you'll find a little bit right at the end of it. And then it gets into 3.5. And it's also referred to as combustion analysis. You'll see it under that heading as well. Okay, so the idea here is that we are looking at compounds now. So let's remind ourselves what a compound is. A compound is one of the two types of materials that are called pure substances or just substances. Okay, so sometimes people call it pure substance, people just call it a substance. Okay. And remember, the other type of pure substance is called an element, right? And the elements are those materials that are in the periodic table. Okay, what differentiates a compound from an element, they're both pure substances, is that a compound is a combination of elements, right? It's a combination of elements. So I'll call it combined elements. So for example, you might have one element, which is hydrogen. And you might have another element, which is oxygen. And those two elements can combine to form a compound. In this case, water, right? So this is the compound. It's combined elements. And one thing that's interesting about compounds is that their behavior, their properties, are different from the elements that make them up. So hydrogen and oxygen have certain properties in terms of how they behave, but water is very, very different, even though it's made out of hydrogen and it's made out of oxygen. It's a different type of substance, so we call it a substance, all right? So what we're going to do in this topic, in this discussion, is we're going to figure out what is the formula of a compound given percentages of each element in the compound. Okay, and these are really, we're talking about mass mole calculations. That's really what this is. It's just another example of mass mole calculations. So the idea would be the following. Suppose you had some sort of material, some substance here, and it's made out of a bunch of different molecules, and you're trying to figure out what that substance is. You know, is it glucose, which has a formula C6H12O6? Is it sucrose, which has a formula C12H22O11? You're trying to figure out what that substance is. And the way we're going to do this is we're going to do what's called elemental analysis. Okay, so that's the idea, is to figure out what a substance is based on some information, on some data that we're given about the substance, about the compound. Okay, now there are different ways of presenting the data, but the most common way is percent by mass. So that's the examples we're going to look at today are where they give you percent by mass. So for example, you might see, 35% oxygen and 55% carbon and 10% hydrogen. Okay, so what you're getting in terms of the data that's given, this is the given data, are percentages that add up to 100, right? If you add these up, they add up to 100%. So if they add up to 100, that means those are the only elements that are in the compound. If they didn't add up to 100, let's say you got 95, that would mean there's some other element in there probably, maybe a fourth element, okay? And these are percentages by mass. So what does that mean, percentage by mass? What it means is it's the mass of the element that we're talking about divided by the total mass times 100%. Okay, so these numbers, when you see them, 35% oxygen or 55% carbon, what that means is the mass of oxygen divided by the total mass times 100 is 35%. The total mass is the molar mass of the compound. Okay, that's how much 1 mole, it's the mass of 1 mole of the compound. Right? Remember, that's what the molar mass is. It's the mass of 1 mole of a substance, generally a compound. Okay. So let's take a look at an example here. The first one we're going to look at is actually pretty simple. So let me find the numbers. It's hard to make these ones up because you got to have the numbers just right. So this is called, in your ALEKS homework set, this is called elemental analysis of binary compounds. Okay, let me make this a little bit smaller. There we go. Move this over. There we go. Okay, so in this example, what they do is they say you've got a compound X. So they call it compound X, meaning you don't know what that compound is. And then they tell you it has the following composition. So they give you the name of the element, and then they give you the mass percent. Okay, so the first one is nitrogen. And the second one is oxygen. So those are the only 2 elements in this compound. And the mass percent is 26.0% and 74.1%. Okay. And then they want you to calculate, so find the empirical formula. Okay, find the empirical formula of compound X. Okay, so let's talk a little bit about the empirical formula. The empirical formula is a representation of the ratio of the elements in the compound. Okay, so the empirical formula should look something like this. It should have the symbol, the first element, which is nitrogen. It should have the symbol oxygen, which is the second element. And then it should have some numbers underneath it. So the numbers might be 1 and 1, in which case you wouldn't write anything, right? In a chemical formula, if the number is 1, the number of atoms is 1, you don't write anything. Or it might have 1 and 2. Or it might have 2 and 1. Okay? Now, one detail about the empirical formula is that it's the smallest whole number ratio. Okay, just the nature of what it is. It's the smallest whole number ratio. So for example, if I had N2O4 as a formula, that ratio, 2 to 4, is not the smallest ratio possible. Oxygen is twice what nitrogen is, 4 to 2. So to change that to the empirical formula, we would just say, oh, just divide this by 2, divide this by 2, and you'd get NO2, and that would be the empirical formula. So it has to be like the smallest whole number ratio. So 2 and 4 wouldn't work. If you had like 3 and 6, that wouldn't be an empirical formula because you could divide each of them by 3 and get smaller whole numbers. That would be an empirical formula. Okay. So when you do this problem, you're going to get the empirical formula out of it. It's got to be the smallest whole number ratio, but don't worry about it because when you do it, when the problems are set up this way, it'll work out as the empirical formula. So here's the approach. Let me just erase all of this down here so you can see how you go about this. This is all mass calculations, just like what we did back in section 3.4. Really, it builds on that section. So here's how you do it. You look up each element. So nitrogen is N, right? So you look that up. That's the symbol. And then you look up its molar mass from the periodic table. Remember, the molar mass is in grams per mole. That's the units. How many grams 1 mole weighs? So you look it up for nitrogen, and it's 14.01 grams per mole. You look up oxygen. Oxygen is O, and its molar mass is 16.00 grams per mole. Okay, so those are the molar masses of the two elements. Now we do the percent composition of each element separately. So you do each element separately. Doesn't matter which one you do first. You've got the data to do both of them. So I'm just going to pick nitrogen because it was the first one that was given. So I'm going to pick nitrogen. Here's what you do first. Convert percentages to grams. Okay, so notice how it's given in percentages. Now, how do we do this? How do you convert a percentage to gram? In fact, you can't really convert a percentage to gram, but here's what we do. We assume that there's 100 grams of the compound. Compound X, right? If there is 100 grams of the compound, 26% of it would be nitrogen, right? That's what the mass percentages are telling us. They're telling us what amount of each element out of the whole percentage, 100%, is due to each element. So if you have 100%, or I'm sorry, if you have 100 grams of the compound, 26.0% of that 100 grams has to be the nitrogen. Well, 26.0% of 100 is 26.0. So that means you've got 26.0 grams of nitrogen. Okay, so you just essentially say, look, because these add up to 100, that means we can assume we have 26.0 grams of nitrogen and we have 74.1 grams of oxygen, and then that will work. So there's our first step. So one is you assume you have 100 grams of the compound. That means you've got 26 grams of nitrogen. Step 2, convert grams to moles. Okay, now we did that last week. Luckily, we had a weekend to kind of mull it over and think about it and work on problems. Converting grams to moles is something we covered in the previous section. It's a very standard type of calculation. So here's how we go about it. We take the mass that we have, 26.0 grams of nitrogen, and we use the molar mass. Remember what we said? You divide by the molar mass to get the number of moles, or you write it out like this. 1 mole of nitrogen is 14.01 grams of nitrogen. So see, when you do it that way, you are in fact dividing by the molar mass. You're taking 26 and you're dividing it by 14.01. And so I'm going to leave an extra sig fig, 1.856. Let me show you the sort of the way you deal with the sig figs here. This is a kind of practical issue. The calculation we just did is division. And the rules for sig figs is you take the measurement that you have. So that one, you count the sig figs in. So that's got 3. You take the other measurement, that one's got 4. The answer should have the smaller of the two. So the smaller of the two is 3 sig figs. So our answer would be 3 sig figs. But we're going to use that number, this result, in a subsequent calculation, in the second calculation. So we don't round it yet. So I'm going to write in here, don't round it to 3 sig figs yet, because we're going to use it in a subsequent calculation. If the question was in 26 grams, how many moles of nitrogen is it? Then you would round it, because that would be the answer. So you'd round it to 3 sig figs. But because we're going to use this in another calculation, you keep 1 extra sig fig. You can keep more than 1 if you want to. That's perfectly fine. But keeping 1 extra sig fig usually works fine. Okay, so there's your 1 extra sig. Okay, we got the number of moles. So now step 3, we're going to work on oxygen. You work on the next element, which is oxygen. So for oxygen, same thing. We're assuming we have 100 grams. So you've got 74.1 grams of oxygen, right? You're assuming 100 grams of the compound X. So that means you've got 74.1 grams of oxygen. Step 4, convert grams to moles, just like you did with the nitrogen. Convert grams to moles. Grams to moles, divide by the molar mass. So 74.1 grams of oxygen divided by 16.00. Okay. So you're not going to get a whole number. At this stage, you won't get whole numbers. You're going to get these decimal numbers. So 74.1 over 16. And you get 4.63. Again, I'm going to keep 1 extra sig fig. See how this one has 3, this one has 4. So keep 1 extra. So that would be moles of oxygen. Okay. Now here's what we have. Here's what we've got here. This is the number of moles of nitrogen in the compound. This is the number of moles of oxygen. See how they're not whole numbers? At this stage, they generally are not. They're not going to be whole numbers. So what we do is we try to turn them into whole numbers. And here's the first step in doing that. If you take a number and divide it by itself, you'll get 1, with the exception of 0. So 8 divided by 8 is 1. 12 divided by 12 is 1. 4.631 divided by 4.631 is 1. So what I'm going to do is I'm going to look at the smaller of the value, the smaller of the two values. So this one's smaller, this one's larger, right? I'm going to divide both of them by the smaller. Okay, so let me make a little room up here. So divide by the smaller. The smaller one is nitrogen. So what I'm going to do is I'm going to take nitrogen and I'm going to divide it by itself. That will give me a whole number for sure. It's going to give me 1. Just dividing it by itself. So when you do this step, you'll always get 1 for the smaller one. Now we divide the larger one by nitrogen. Okay, you're dividing both of them by the smaller. So 4.631 divided by 1.856. Okay, you might get a whole number here, but you might not. So you're just gonna have to check and see. So 4.631 divided by 1.856, you get 2.495. Okay, now what I've done is just a little mathematical trick. What I've done is I've said I'm going to divide these two numbers by the smaller of the two just to get a ratio. So it would be kind of like this. If I said I had, 500 hats and I had 100 shoes, and I wanted to know how many hats I have for every shoe. What I would do is I would say divide both of them by the smaller of the two. And then you take 100, divide it by, sorry, not 1,000. 100 shoes divided by 100 shoes. And that would give me 1, right? See how you always get 1? Because you're dividing them both by the smaller. What that would tell me is 2 pieces of information. It would tell me that for every for every shoe, I have 5 hats, right? 500 to 100 is the same as 5 to 1. So really all I'm doing is I'm just making the number smaller to get a ratio, okay? The reason for this is that the empirical formula is the smallest ratio. So for example, if we were using hats and shoes, it would be 5 hats for every 1 shoe. That would be the molecular formula, the empirical formula of this ratio of hats and shoes. You're just trying to find out what they are relative to each other without using these big numbers like 500 and 100. Same thing here. 1.856 and 4.631, they don't work for an empirical formula because they're not whole numbers. So we try to turn them into whole numbers. How do we do that? By dividing by the smaller of the two. And that gave us 1 whole number. That's a whole number. This one's not, though. That's not a whole number. It's not a whole number. So sometimes when you do these problems, you're going to get that one of the elements is not a whole number. So how do we deal with that? So that's one additional step. Notice this is very close to 2.5. It's almost exactly 2.5. Okay, so here's what we do. We look at that number and we say, hey, that's really close to 2.5. So that means it's 2.5. So that means that our ratio is you have 1 nitrogen and for every 2.5 oxygens. Now, again, that's still not a whole number, but how do you turn a whole number? How do you turn this into a whole number? The goal is to get small whole numbers for the empirical formula. So here's what you do. You say, is there any small number, the smallest number I can think of, that I could multiply this by to get a whole number? That's the logic you're using now. Is there any small number I could multiply 2.5 by to get a whole number? Now, you could multiply it by 10, and that would give you a whole number, right? 2.5 times 10 is 25. That's a whole number. But we want the smallest possible number to multiply it by, because we want these in the empirical formula to be really small numbers. Remember, N2O4 is not an empirical formula, but NO2 is. So the smallest would be 2. If you multiply 2.5 by 2, that's going to give you a whole number. So I'm just going to multiply this by 2. But we want the ratio to be the same. So if I multiply this one by 2, I got to multiply this one by 2. 1 times 2 is 2. 2.5 times 2 is 5. Those are whole numbers. Now, those are the smallest possible whole numbers. So we're going to have our answer, N2O5. And that would be our answer right there, N2O5. Okay, So we check and we say, hey, is there anything we could divide those by to make them smaller but still be whole numbers? And the answer is no. If you divided them by 2, that would give you 2.5. That's not a whole number. So divided by 3, that wouldn't work. Divided by 5, that wouldn't work. Anything 2 or greater would make them, at least one of them would not be a whole number anymore. Okay, so there you go. So that's elemental analysis of a binary compound. I'm going to show you another one because that's the first one we've looked at, and this is maybe the first type of problem we've looked at where there's multiple steps and you have to kind of map out a strategy. The other problems we did were pretty basic, right? Like here's the number of grams, how many moles, here's the number of grams, how many atoms is it? That's only like 2 or 3 steps. This one involves multiple steps. There's a bunch of steps in this problem. We'll get to other problems that are multiple steps. So let me show you another example, okay? So again, our answer would be N2O5. So here's one. Let me just bring this one up. This one's just called elemental analysis. Okay. So again, it's this problem where you have compound X and they give you the elements. So this one's chlorine. And the next one's oxygen. So just 2 elements. And then they give you the mass percent, 38.7, 61.2. And then I'm going to go ahead and put the symbol and the molar mass for each element. So I'll do this part. Okay, chlorine, you look that one up, it's Cl. C is carbon, chlorine is Cl. Molar mass of chlorine is 35.45. Oxygen, 16. Okay, and again, we want to find compound X. What's the empirical formula? Okay. Same idea. So here's what we do. We look and we see, do these percentages add up to 100? Did I get that number right? That actually looks off a little bit. Oh yeah, they did. So sometimes when they make these problems, they'll play around with you a little bit. If you add these up, you get 99.9%. So there's a little bit of error in there. E-R-R-O-R, not air that you breathe, but mistake, right? So you'll see that sometimes. Sometimes they don't add up exactly to 100. So you can say, well, was there a third element? And the answer would be no. There is no element that would weigh so small that it would be 0.1%. So you just have to go with these numbers. You just have to, essentially what happened was, it's really 38.74 and 61.26. So they rounded them off to where you lost some of the values, so it only adds up to 99. But again, just assume it's 100%. Okay, so let's take a look. I'm going to do the first one, which is chlorine. So step 1, you divide by the molar mass to get the moles. So you assume there's 38.7 grams. Divide by the molar mass. And then you see what you get there. Again, you won't get a whole number here. .09, and again, 3 sig figs, so I'm going to add 1 extra, so 0.92 moles of chlorine. And then you do the same thing for the second element. If you have 3 or 4 or 5 or 6 elements, you just do the same thing for each of them. Get the number of moles of all of them. So oxygen, 61.2. 1 mole of oxygen, 16.000. Okay. Remember, the grams divided by grams cancel, and you get moles. So 61.2 divided by 16.00, 3.825. Again, I'm keeping one extra sig fig because this is an intermediate step. Now the next step is divide by the smaller. Okay, the smaller one's the chlorine, right? So I'm going to take chlorine divided by chlorine. So that would be 1.092 moles divided by 1.092 moles. That's going to give you 1 every time. Whenever you divide something by itself, you're going to get 1. But let's do the oxygen divided by chlorine. Now, technically, you could do the smaller divided by the larger. That would work too, but I don't recommend it. It just adds an extra step. Now, this looks like it's going to work out to be a whole number. I'm just kind of looking at it, just mathematically. It looks like it'll be a whole number. So 3.825 divided by 1.092. Oh, it's not. I was wrong. My math was off. It's 3.503. See, that's not a whole number. But it's very close to a half, right? It's right there around 0.5. So what do we do if it's about 0.5? You multiply them both by 2. So this is to eliminate the 0.5. 2 times 0.5 is a whole number. So we have Cl is 1, so we're going to multiply that by 2. Remember, you have to multiply both of them by 2, not just 1, or you change the ratio. So 3.5 times 2 is 7. Okay, so you got 2 and 7. Those become the subscripts. Those numbers, after you multiply by the 2, become the subscripts. So you got Cl2. Generally, you write the element they give you first at the top here. In general, oxygen is written after other elements. So if you have sodium and oxygen, you write the symbol for sodium and then oxygen. Oxygen you usually put at the end. So Cl2O7. And that right there would be your empirical formula. Okay. So there are machines that you can buy. There are analytical devices you can buy that will give you the percentages. You grind it up into a powder, your sample, or you put it in as a gas, and then out will come some percentages from the instrument. It'll tell you what the percentages are. And if you have that, then you have these percentages. So then you can do a quick calculation like we just did right here and figure out what the empirical formula of the compound is. Okay. So there you go. So there's a couple of examples of that. Let me show you one more, if I can find one more, where you have, let me see. Close that one off. I guess I can't find one. I thought I would be able to find one. Oh, here's one. Okay, so every once in a while you're gonna pop up with one of these where they give you 3 elements. So I do want to show you 3 elements. So again, this is elemental analysis. So I was scrolling through examples of the problems, and I couldn't get one with 3 elements, but I know I had seen one. So I just wanted to find it. So the first element is carbon. I like this one because it's an organic compound. And you get your mass percent, 63.2, 5.31, 31.6. And again, these are all percentages. You want to find the formula for the compound. Okay, come back over here. Okay. So let me go ahead and put the symbol and the molar mass. So carbon is a C, hydrogen is an H, oxygen is an O, and then you look up their molar masses, 12.01 grams per mole, 1.01 grams per mole, and then 16.00 grams per mole. Okay, so notice you got 3 elements here. So again, they should add up to 100%. They don't here. I'm looking at these numbers and they're close again. It looks like it's, oh, that's a 31. It looks like they're going to add up to 99.9. Let's just check just to make sure. 63.2, 5.31, 31.6. Oh, they're actually a little bit over. A little bit over. It's 100.11. Okay, so again, that's just the rounding issue when they made the measurements. It wasn't exactly 63.2. It was probably 62.95 or something like that. So they're just because of the way they rounded it. Also notice that hydrogen goes an extra digit past the decimal point. They're just trying to make sure that it has 3 sig figs. Hydrogen is generally pretty small percentages because it doesn't weigh very much. So because it's only at 5, they went 2 digits past the decimal point. Okay, same idea. The difference here is you've got 3 elements, so you just divide by the smallest number of moles for the 3, right? And the other one we only had 2, but now you got 3. So you just divide by the smallest. So let's do carbon first. Again, even though it doesn't add up to 100, it's pretty close. So there's your number of grams. Divide by the molar mass. Okay, so 63.2 divided by 12.01 is 5. 1 extra sig fig, 262. Do the hydrogen. 5.31 grams of hydrogen. 1 mole of hydrogen is 1.01. Okay, so 5.31 divided by 1.01 is 5. Now that number right there is almost the same as carbon. If you look at them, 5.2, and then the third digit is a 5 versus a 6. If you rounded hydrogen up, you'd have 5.26. If you rounded carbon, you get 5.26. So those numbers are going to be the same. So throughout the whole calculation, in the end, carbon and hydrogen will have the same subscript. And then you do oxygen. Oxygen is 31.6. 1 mole of oxygen is 16 grams. Okay, so 31.6 over 16. 1 point, now that's smaller, right? That one's the smallest of the 3. That one's the smallest. So you're going to divide by oxygen. And then, like I said earlier, usually you put oxygen at the end. So if you have carbon, hydrogen, and oxygen, the formula is usually written in the order carbon, then hydrogen, then oxygen. That's typically how it's done. Okay, so let's divide all by 3. Divide all 3 by oxygen. So carbon divided by oxygen is 5.262 over 1.975. Doesn't look like a whole number to me, but let's see. 5.262 divided by 1.975. 2.66. This is interesting. 2.664. That's not moles, actually. It's unitless, right? Moles divided by moles is unitless. Okay, let's do the hydrogen by the oxygen. Remember, you can divide them all by the smallest. 5.257 over 1.975. Again, you're not going to get a whole number here. It's going to be very close to the first one because the numbers aren't that different. So it looks like you got 2.661 or 2.662 actually. And they're only differ, these two only differ in the fourth significant figure. They're very close to each other. And then, of course, oxygen divided by oxygen. You don't really have to work this out. This is going to be obvious. It's 1, right? 1.975 divided by itself. That's just going to be 1. So 2 of them are not whole numbers, though. So now, again, I want to be careful at this stage. The biggest mistake I think that people make in doing this kind of problem is they say, look, that 2.66 is pretty close to 3. So I'm just going to round it to 3. And that's no good because it's actually very, very far from 3. So think of your number line. If you had 2 and 3, here's 2.5. 2.66 is like right around there. That's actually very far away. If your choices are 2 or 3, you're not close to 2 and you're not very close to 3. So generally, if we were at 2.95, then that's around 3. If we were 2.85, you're not at 3. You can't round 2.85 to 3. So here's what you do. You look and you see, is the first digit past the decimal point 9 or greater? If it is, then generally you can round it up. But if it's not 9 or greater, you can't round it up. Likewise, if you had 2.01, if the first digit past the decimal point is a 0, then generally you can round it. But if you had 2.1, generally you don't want to round that one either, okay? So notice 6, that is not 9 and it's not 0. So do not round. Don't round at that stage. Okay, so here's how you deal with it. We deal with it very similarly to how we dealt with the 0.5. So if I have 0.5 and I multiply it by 2, that gives me a whole number, right? So for example, 1.5 times 2 is 3. If I have 0.66 and I multiply that by 2, that doesn't give me a whole number. But if I multiply it by 3, right? Because this is really 2/3. So if I take 2/3 and I multiply it by 3, that gives me a whole number. Okay, so what you're going to do at this stage is you're going to look at those digits that come after the decimal point. And if it looks like it's around 0.66, you would multiply by 3. So let me multiply these by 3. So 2.66 times 3. And you get 7.992, which is about 8. I'm going to multiply this one by 3. 2.662 times 3. And you get 7.986, so very close. So you get about 8. But remember, you got to do them all. So 1 times 3 is 3. Okay, so see how these numbers worked out, 8, 8, and 3. Those are definitely whole numbers, and there's no way you can divide them by some number to make them smaller. So those would be the empirical formula. So C, this becomes the subscript 8. H, this becomes the subscript 8. And then O, that becomes the subscript of 3. So there's your empirical formula. And you're set. You've got it there. Okay. All right. So in this case, we had to multiply by 3. What I want to do is I want to kind of give you the arithmetic of what you multiply it by. Oops. Every once in a while I hit the wrong button. Okay. So if you have the ratios, so for example, you've got, one of them is going to be 1, right? And then you've got some numbers here. You don't know what they are. I don't know what they are, but M and N. I'll just use the symbol M and M to represent the numbers that we have there. Okay. If M and N are 0.5, so if they're around 0.5, so like 2.5, 3.5, 4.5, you multiply everything by 2, and that'll give you a whole number. If you have 0.66, multiply it by 3, and that will give you a whole number, right? The reason that works is 0.5 is really a half, and 0.66 is really 2/3, okay? If you get 0.25, multiply this by, well, think about it. What is 0.25? 0.25 is 1/4. So multiply by 4, and that will give you a whole number. Now here's another possibility, 0.33, if you get 0.33. Well, 0.33 is a third, so it's kind of like 2/3 in a way, right? You multiply by 3, and then that'll give you a whole number. Let's say you had 0.2. Well, that's 1/5. So you multiply that by 5, and that'll give you a whole number. And if you have 0.17, that's really a 1/6. So you multiply by 6, and that'll give you a whole number. Okay. Now, generally, you're not going to see many problems where they go this far. Generally, you're going to see ones where it's ×2, or maybe ×3, or maybe ×4. You'll see those. These are relatively rare occurrences that you'll see that, but that's how you would deal with it. If you had 0.14, that's 1/7. So you'd multiply by 7, and that would give you a whole number. Okay. So just to remind you, if you're in a situation where you've got, let's say, 1 there, and you've got, I don't know, 3.91, if this is a 9, then you can round it. Okay, just round it to 4. You don't have to multiply it by some number to get it to a whole number. But if you have, 3.75, let's think about 0.75. Well, 0.75, that's 3/4, right? That's the fraction 3/4. So you multiply by 4, and that'll give you a whole number. Okay, so 3.75, we want to multiply by 4. And then that would give us, well, 3.75 times 4 is 15, right? So be careful. Look at what you have in terms of these numbers. If it's 0.9, then you can just round it. But if it's less than 0.9, you want to figure out what you got to multiply it by to get that whole number. And then make sure you multiply all of them by the same number. So you're going to multiply the 1 by 4. You're going to multiply the hydrogen by 4. And then you're going to multiply the oxygen by 4. Okay, they're kind of fun. These are nice little problems. And if you have any questions about rounding, like when do you round and stuff like that, just let me know. Okay. All right, let me show you one more. We have really just enough time for one more problem. And that's about right, because this section is just about done. So this section is, or it's the same section, but this type of problem, this topic is called finding the molecular formula from the molar mass and elemental analysis. Of a binary compound. So let me show you the example here. They tell you again, it's very similar to what we just did. It's compound X. And here they tell you the molar mass, they give this to you. That's the key here. If they give you the molar mass, then you can do this type of problem. If they don't give you the molar mass, then you just do the empirical formula like we just talked about. So here's your 2 elements, phosphorus. So these are 2 elements that can combine with each other. And then they give you the mass percent is oops, sorry, let me just erase this. 14.87. and 85. So in this case, they do add up to 100, so there's no rounding error here. That doesn't necessarily mean the problem is going to be all that different, but so there's your symbols. And then phosphorus is 30.97 grams per mole. So see, we're really just doing this just like we did the other one. It's almost identical the way you approach this. There's just going to be one additional step at the end. So let's go through it just like we did before. What we did was we said you assume you have 100 grams, right? 100% meaning you have 100 grams of the compound X. So 14.87 grams of phosphorus divide by the molar mass. So I'm not doing this any differently so far. There's only going to be really one difference at the end. So 14.87 divided by 30.97, 0.4801. Now, actually, I got to keep one more digit, right? Because this has, they gave us 4 sig figs in the measurement. So I'm going to keep one more. So that'd be 5. That's interesting. And then same thing for chlorine, 85. They gave us 4 sig figs. So 85.13 divided by 35.45, and you get 2.4014. That's interesting. Are they going to be a whole number when we take the ratio? I think not. It doesn't look like it will be, but we'll see. Maybe it is. So the smaller one's this one right here, phosphorus. So do them by phosphorus. So phosphorus over phosphorus is 1, right? If you divide something by itself, you're going to get 1. That's easy. But now let's try the chlorine divided by phosphorus, right? Remember, bigger by smaller. 2.4014 divided by 0.48014. Okay, so let's see what that works out. 2.4014 divided by 0.48014. Oh, almost exactly a whole number. 5.000015. That is a whole number, right? Like I said, if it's 0.0 or 0.9, no need to multiply it by a number. If I got 0.75, then I'd need to multiply everything by 4. Okay, so we're set. That's 5. So that step is easy. We don't have to do that extra step. So here's the empirical formula. Empirical formula is you had 1 phosphorus, so P, and then 5 chlorines, so Cl5. PCl, yeah, that's right. That's PCl5. Okay. Okay, so there's our empirical formula. Now, last step, we want to find the molecular formula from the molar mass. So the key here is they got to give you the molar mass. Curious that we'll see if this is what happens here, but okay, so 416. So here's what 416.48. Let me write that down. There we go. So I'm going to save this one and then open up a new one. Okay, so here's what we have. The empirical formula is PCl5, right? And the molar mass is 416.48 grams per mole. We want to find the molecular formula. Okay, now the molecular formula is the actual number of atoms for each element in the compound. I'll just write X for compound, okay? So let me show you what I mean by that. Suppose I had N2O4. This is 2 nitrogens and 4 oxygens. Okay, this is the molecular formula. But remember what we said about the empirical formula? It's the smallest ratio of whole numbers. So 2 to 4, you would divide them by 2 and you'd get 1 and 2. This would be the empirical formula. So the empirical formula is, in a sense, the reduced value of, it's the smallest whole number ratio. So the actual structure of N2O4 looks like this. There's 2 nitrogens, and each nitrogen has 2 oxygens coming off of it. That's the actual structure of N2O4. So the molecular formula shows how many nitrogen atoms are in there. There's 2. And how many oxygen atoms are in there. There's 4. That's the molecular formula, N2O4. The empirical formula just says, look, how many oxygens are there for every 1 nitrogen? Well, if you have 4 oxygens and 2 nitrogens, it's a 1 to 2 ratio. 2 to 4 is the same as 1 to 2, okay? So now we've got this, we know it's NO2, in this case it's PCl5. Now we want to figure out what the molecular formula is. And here's how you go about it. Let me just show you here. It's very simple. The molecular formula is a multiple of the empirical formula. So what I mean by a multiple is it's 1 times the empirical formula, or 2 times the empirical formula, or 3 times the empirical formula. So for example, if it's 1 times the empirical formula, 1 times 1 and 5 would be 1 and 5. So it can be the case that the empirical formula and the molecular formula are the same. They can be the same if the multiple is 1. But it can be twice as much too. So twice as much would be P2Cl10, twice as much. Or it could be 3 times as much. P3, 3 is 3 times 1, 15, right? 3 times 15, 3 times 5 would be 15. So the molecular formula is going to be something like this. It could be the same. It could be the same, but it could also be multiples. So here's how you go about it. What you do is you ask yourself, how much does the empirical formula weigh? What's its weight? So you got 1 phosphorus. So 1 times 30.97. And you got 5 chlorines, 5 times 35.45. And you just add them up. So those are the molar masses from the periodic table. So 30.97 plus 5 times 35.45, and you get 208.22 grams per mole. So what you're doing is you're asking, what's the molar mass of the empirical formula? And you're going to get a number. Then what you do is you take the molar mass of the molecular formula. That's the one they give you. So that's that 416. That's the molar mass they give you. And you divide it by this number you just calculated right there, the molar mass of the empirical formula. And you're going to get a whole number. It should be a whole number. So 416.48 divided by 208.22, and that gives you almost exactly 2. Okay? If it's a 1, that means the molecular formula and the empirical formula are identical because they have the same molar masses. They got to be the same compound. But if you get a ratio of 2, that means that the molecular formula weighs twice as much as the empirical formula, right? This is 2 times what that is. So if it's twice as heavy, that means it has twice as many atoms. So you say, okay, well, here's our empirical formula, PCl5. What would that be times 2? It's got to be twice as heavy. Well, that would be P2, 2 times 1. 2 times 5 is 10. So P2Cl10. And this would be the molecular formula. Okay, and there you go. That's the last type of problem in this section 3.5. We just really have stoichiometry and limiting reactants to go through, so we can start working on that tomorrow. But try a couple of these, right? Try the 2 different types. Try the finding the empirical formula, and then try the finding the molecular formula. Again, the molecular formula problem, they got to give you the molar mass of the molecular formula. And again, if these numbers are equal, then your molecular formula is the same as the empirical formula. But often it's heavier. Okay. So we're not going to go through this, but there are instruments out there. You can Google them and look them on YouTube. There are machines that will actually just measure the molecular mass for the molar mass of the molecular formula for you. They'll just give you the number. It's just a printout. So it weighs 416.48. So with that information, you can then figure out what the molecular formula is. And again, that's what the goal is, to figure out the molecular formula. Okay. So interesting type of problem. It's the first type of problem, I guess I would say, where we have a lot of multiple steps that you have to do. And you have to do some reasoning in there and figuring out how you're going to round and whether you're going to round and then assess. Okay. So I'll have this up on YouTube within an hour or two. And reach out to me today or tomorrow. Tuesday is actually a pretty busy day, but I certainly have a few minutes here and there. Wednesday's a lot lighter. Thursday and Friday get very light for me. So feel free to reach out this week if you have any questions. Otherwise, have a great day, you guys.
Thank you, Professor. Have a great day.
Thank you.
Au revoir.
Bye.